Hello, everyone. Good evening, and welcome to this very special lecture series of the ICTS, the Ramanujan lecture series, which has been supported by the Infosys Foundation for several years. This is one of our flagship lecture series, together with the Chandrasekhar series, the Infosys Chandrasekhar series in the physical sciences, the Ramanujan in the mathematical sciences, and the Turing lecture series, which is in computer science and also biology, engineering related topics. So it's a very, this lecture series has had a number of very distinguished speakers, and I'm very thrilled that Professor Nigel Hitchin could accept our invitation to be here to give these lectures and to be part of this larger meeting that we are having this week and next week. And for me particularly, it's I've been as a string theorist, not a mathematician, but I have been also inspired by and have used Professor Hitchin's work, the ADHM construction, and many other things, including and also been inspired by the work on monopoles, the Hitchin-Atiyah paper, and on the Yang-Mills on Riemann surfaces and so on. But I leave the more technical introduction to Oscar, and it's again, I extend my welcome to Professor Hitchin and looking forward to his lectures. I'll now invite Professor Oscar Garcia-Prada to introduce the speaker.
Thank you very much, Rajesh. It's a pleasure to introduce Professor Nigel Hitchin, Emeritus Civilian Professor in Oxford. And for most people here, he doesn't need any introduction, but let me just say he is indeed an essential figure in the field of geometry, more concretely in the interaction of differential geometry with algebraic geometry and equations of theoretical physics. Rajesh mentioned some subjects like the ADHM abstraction and monopoles, but there are other fundamental contributions of Nigel's like Higgs bundles that is the subject of this series of lectures. So he has received many honors and prizes, and let me just single out the Shaw Prize in Mathematical Sciences in 2016. And the list is big, so you can look in Wikipedia. And my co-organizer, Pranav Pandit, and myself, and the ICTS, as was expressed, very grateful to you, Nigel, for having accepted these lectures and coming to India and to Bangalore. And the subject of this series of talks is subject of research of Professor Hitchin. Is not so close to Ramanujan, but there is a very special connection between Ramanujan, yeah? oh, I shouldn't say.
Wait 5 minutes, yeah.
All right, okay. So, all right, so instead of you'll be curious to wait for the special connection, I'm very often a spoiler. I have a reputation of that. So, but this time I will resist. Okay, so with no further ado, I think that I think you have something to, there is something that Rajesh is going to give to Nigel.
On behalf of ICTS, a small memento, a poster of your thing, a sweatshirt, and a mug.
Oh, thank you very much.
And so we have the first lecture, I believe, is the integrable system. He calls it the integrable system, but everyone calls it the Hitchin integrable system.
Okay, well, thanks, Oscar. And I'm sorry to spoil your introduction, but you know, okay. So it's a great honor for me to be invited to give these lectures and to come back to India, which I was only here in 1991. That's the only previous time I've been here. So yes, so I'm going to give these 3 talks about different aspects of Higgs bundles. But these are the Ramanujan lectures, and so here is Ramanujan, and this is, so I gave a lecture in Cambridge last year, and I went into Trinity College Chapel, and this is the memorial to Ramanujan. You'll see those who can understand Latin, that he was the first Indian to be elected as a Fellow of the Royal Society. And right next to that memorial are two more. There's Hardy and Littlewood. And so, again, actually, my Latin is pretty bad, but this vir opinionem impatiens alienarum, that sounds pretty tough, you know. I think it means rigorous. So Hardy was a rigorous mathematician. So as Oscar says, as I say, my mathematics has not really been influenced by Ramanujan. On the other hand, there's a sense in which I'm descended from him. So now, this is what Oscar was going to say. So here you see, so Hardy left Cambridge because he was a pacifist during the First World War and went to Oxford. And then he created a chair for Littlewood, effectively the first Rouseball professor. So this is my descent from Ramanujan. Okay, so this, I'm going to talk about three different aspects of Higgs bundles. And I want to begin with this, the integrable system, which nowadays goes by my name. The second one will be a talk about my approach to the universal moduli space, which intersects quite a lot with the talks we've been hearing from Brian Collier. And finally, I want to talk about what I call the odd integrable system, which is something which I've been trying to get people interested in for a long while. And there doesn't seem to be a market for it in England or in Spain, so I'm trying India. Okay, so let me begin. Let me just say what I mean by an integrable system. So I mean a complex symplectic manifold with n functionally independent Poisson commuting functions. So that means that if I take any function of these FIs, that will define a Hamiltonian vector field, and then the FIs are constants of the motion. So for example, the most famous one is perhaps the geodesics on the ellipsoid. The symplectic manifold is the cotangent bundle of the ellipsoid. One of the functions is given by the metric, but there's another quadratic function. It turns out that these two Poisson commute, which means you can solve the geodesic problem on the ellipsoid, which is typically a very difficult problem to solve. But that's it. So it's not really the mechanics of particular flows which I'm interested in, but a naturally occurring integrable system which fits in with lots of previously existing ones. But what I thought I would do was to start with a little history about how it came about, what was the original context, and what was the context basically of the Higgs bundle moduli space, and how did the integrable system fit in with that. And then what I'll do is look at ways in which, since the original paper, ways in which the integrable system has kind of found a way to make its presence felt in the Hyperkähler geometry of the moduli space itself. So all along the road, I've been influenced by talking to physicists, and perhaps that might become apparent as we go along. So first we go back to 1983-84, when I spent an academic year in Stony Brook in the mathematics department, but I found myself talking to Martin Roczek from the physics, string theorist, and he was explaining to me the way in which he was able to, using supersymmetric ideas, able to, this was the way that Blaine Lawson explained it to me, take a representation of the group, turn a handle, and come out with a Hyperkähler manifold. I was very interested in how could one do that. And so what it turned out was that this was a version of the quotient construction in symplectic geometry. So let me recall for you what a Hyperkähler manifold is. It's got three complex structures, I, J, and K, which commute or behave like the famous quaternions that Hamilton scratched on the bridge in Dublin. And associated with those three complex structures are three Kähler forms, omega 1, omega 2, omega 3. So we consider those as symplectic forms. And now if we have a group acting and preserving the symplectic forms, then under good conditions, there's a moment map for each one of these. So there's a moment map which takes values in the dual of the Lie algebra, tensored with R3, if you like, tensored with the imaginary quaternions. And the construction says that if we look at the inverse image of 0 under this and divide out by the group, then we get another hyperkähler manifold. And the miracle from what Martin was doing was to start with flat space and a symplectic representation, and then get out of it some, at the time, known hyperkähler manifolds and unknown ones as well. And this all fitted in with supersymmetric ideas well. But for me, it was an interesting construction of something I've been interested in for a long while. So after that year, so the summer of '84, I went back to Oxford, and Michael Atiyah immediately got onto me because he wanted to use this in an infinite dimensional context. Because he'd been using, so his famous paper with Bott on the Yang-Mills equations on the Riemann surface had this formalism of symplectic reduction, but for an infinite dimensional space, justified by some analysis. So what he wanted to do was to do this for the moduli space of monopoles. And in particular, he wanted to try and use some ideas of Nick Manton, another physicist, about the motion of monopoles, of two monopoles in particular, by studying geodesics on the corresponding hyperkähler moduli space. So we didn't know whether it was easy to solve the geodesic equations, but we knew that there was a hyperkähler manifold, that it had a certain group action, rotations, and so there was enough information to try and get the metric and then move on from that to find the geodesics. So that was this infinite dimensional setup. So here you can see what it is. So again, you look at an affine space, just like they did in the Atiyah-Bott paper, but now it's a space consisting of a connection on a bundle, a principal G bundle over R3, and another function, or if you like, a section of the adjoint bundle, which this is where I learned to use the word Higgs fields from the physicists. So typically these, when you do dimensional reduction, the terms which don't appear in the connection seems to be called Higgs fields. So if anybody asks why when we get down to it, is this a moduli space of Higgs bundles? And this is somehow the origin of it, studying monopole. So the quotient construction here says that if we look at the infinite dimensional group of gauge transformations, there's a moment map, and we have the L2 in a product, and the moment map yields automatically the equations for magnetic monopoles, these Pogomolny equations. So that leads to using the hyperkähler quotient construction to a hyperkähler metric on monopole moduli. So by that time, I think, you could see a much bigger picture. So if you went back to the 1970s, 1977 or so, when instantons and self-dual Yang-Mills equations were of great importance, then you could see that actually the moduli space of solutions to the self-dual Yang-Mills equations on R4 that was also a hyperkähler manifold, because you can express it in terms of an infinite dimensional hyperkähler space with a group action on it. And so there's a four-dimensional picture, there's a three-dimensional picture. And so it seemed natural to look at the two-dimensional picture, which is where now we have two Higgs fields and a connection on a two-dimensional space. And the two Higgs fields that you can put together to be a complex Higgs field. And that's what yields these equations, which many of us use, these Higgs bundle equations. Now, in a way, this wasn't new. So in fact, I didn't know at the time, but there's this physicist paper here from 1977. I don't know the name at all. I don't know, does that? No. So he actually wrote down these Higgs bundle equations, as you see. But as you see, unfortunately, it's not interesting. So why is it not interesting? Because if you look for finite action solutions on the R2, and as he says, they don't exist. So I'm going back to thinking, why was it that I decided to look at it on a a Riemann surface. How is it that we can fold it over a conformal invariance? The particular conformal invariance that this has in 2 dimensions has nothing to do with the conformal invariance of Yang-Mills or Yang-Mills. And I think actually I got onto it because of a mistake. So the mistake was this, that I thought it was something to do with harmonic maps. So you can, those same equations, if you put a minus instead of a plus, correspond to actually the equations for a harmonic map into a unitary group. So rather than, for those who know, in the Higgs bundle situation, there is a harmonic map, but into a non-compact symmetric space. With that sign, it consists of harmonic maps into UN. And at the time, there was a lot of information, or the nonlinear sigma model. There was a lot of work done about, for example, harmonic maps from the two sphere into a group or into a symmetric space and so forth. So it was quite natural to once one saw that these were the equations for harmonic maps written in a different form, that one could actually put them on. But pretty soon I realized that actually it was the wrong sign, and so I went on to look at it, and I wrote this paper in '87, which started it all off for me anyway. So it was clearly, it was modeled on, in one sense, on a tier bot, because the title itself clearly echoes the tier bot paper. But also I used a method of proof of Simon Donaldson in his first paper, which was to reprove Narasimhan-Seshadri by using these infinite dimensional points of view. So it was during the producing an argument to give an existence theorem for the self-duality, for these Higgs bundle equations, that this integrable system, or at least the objects which appear in the integrable system, occurred. So if you'll have a bit of patience, let me just go through how it works. So this is, actually we were hearing a little bit about this this morning. So you start with a point of view, this was again a T.R. Bott's point of view, that you start with a C infinity Hermitian vector bundle, and the complex structure is then a D-bar operator, a certain type of operator. These form an affine space, and we're looking at a pair of objects, this complex structure, and a Higgs field. So what we're trying to do is to make this, there is a moment map interpretation for these equations. And what we're looking for is a case where FA plus phi star is equal to 0. So the idea is to look for a minimizing sequence for this function here, if you're on a complex gauge orbit. So look at complex gauge transformations, take one D-bar structure to another one. And the aim then is to find an L2 bound for the curvature, because then you could apply this important theorem of Uhlenbeck on weak compactness. So in 2 dimensions, you don't get any blowing up. You get a nice weak compactness theorem. So what I started to do is I looked at, so first of all, there's a differential equation that the Higgs field satisfies. That means there's a corresponding Weizenbach formula, which gives one inequality. But then here is the point that, so an obvious point really, that if you have a complex matrix, n by n matrix, and if you have a bound on the spectrum and a bound on the norm of the commutator with its adjoint, then that gives a bound on B itself. You know, after all, if BB star is equal to 0, it's a normal matrix, which is diagonalized by a unitary transformation. And then if the spectrum is 0, then the whole matrix has to be 0. So you can argue various ways. I was only working in 2x2 matrices anyway. So, but then on the gauge orbit, the Higgs field changes by conjugation, so its spectrum is actually the same. So on this whole gauge orbit, there is a bound on the spectrum. So when you put the bound on the spectrum together with the bound on FA plus phi star and the Weizenbach formula, then that was enough to give me convergence. But what the upshot of that was that actually this, well, in particular, that this mapping to the spectrum gave me effectively a proper map. I mean, it was, you could use that to, so I'm jumping ahead a bit. If you now have a solution to these equations, then the spectrum, the coefficients of the characteristic polynomial actually give you a proper map on the moduli space. So here, my curly M is the moduli space of solutions to these equations. So it's a Hyperkähler quotient, infinite dimensional Hyperkähler quotient. And the coefficients of the characteristic polynomial give us a map to a vector space of differentials of different degrees. And it turns out that the dimension of that vector space is exactly half the dimension of the symplectic manifold M. And so this is the way it became a completely integrable Hamiltonian system. So let me just say how that happened. In 1985, so soon after I started working on this, I visited Jacques Ortebise in Canada, and he took me up to his, here it is, his cottage in the mountains. It was during the summer, so it wasn't snowy, but I was sitting on the porch there and thinking about this proper map from the Higgs bundle moduli space to this space of quadratic differentials. I was just doing it in. And I thought, well, you know, previously I've been thinking of the cotangent bundle of the moduli space of stable bundles, but then if we have this proper map, then what is the fiber? What does it look like? You know, and that's when I realized that the fiber was actually a torus. So it was this Jacobian of the curve, or a prime variety for SL2. And then it came, you know, to me that, okay, so now I recognize what this is. This is an integral system. When you have a completely integral system with a proper map to the vector space, then the fibers have to be tori. And so, so during the evening there, we thought, so what's the simplest example? And if you remember this, Jacques, the simplest example is the intersection of two quadrics. This is a moduli space. Well, we know that's a moduli space of stable bundles, rank 2 bundles on a curve of genus 2 of odd degree. And so Jacques had written a paper on the intersection of quadrics. So we tried very hard to understand what this integrable system was, and we failed. So it's rather interesting that was 40 years ago. And in those 40 years, actually nobody is, I mean, I had one form of it a few years ago. It wasn't very nice. And then suddenly there was a paper came. Okay, so here let me just, before I show you what it is. So this is the setup. So we've got, the curve is a genus 2. So it's given by this equation. It's a hyperelliptic curve. And we've got these mu i's there. The moduli space, as we know from Newstead, is the intersection of the two quadrics. You can diagonalize one of them to be a standard quadric, and the other one has these coefficients, which are the coefficients in the equation of the curve. And then we're not looking at the full moduli space of Higgs bundles, but we can look at the open dense subset, which is the cotangent bundle of this moduli space. And then on this, there is this integrable system. And it's, so how do we do this? So, okay, let me just tell you that it came through this paper, so the 2024 paper. So this is, you know, nearly 40 years after we struggled to find one. And it's a very beautiful construction. So this is their answer. I'm giving you the answer rather than the way they got it. So if we think of what is the cotangent bundle of the intersection of quadrics, well, first of all, you can take the cotangent bundle of the quadric, and then if you restrict on the base to the intersection, then you'll have the symplectic form is degenerate, so you can divide out by that foliation, and then you'll get the cotangent bundle of the. So this is the first point, that you do all your work on the cotangent bundle of the one quadric, and then you check that what you've got is invariant and in the right way, and descends to the cotangent bundle of the intersection. So you can think of, so there's a cojoint orbit, so this may be the best way to say it. So the equations for the intersection, the cotangent bundle of the intersection of quadrics are those two for x and y, where you divide out by c star, but you can replace that by x wedge y in the Lie algebra. So that's a skew symmetric matrix in the Lie algebra of SO6, and it turns out to be that's a coadjoint orbit. So it's symplectic because it's a coadjoint orbit. And then this is the formula that they give. So you can write it this way in terms of those coordinates. You have to check that these functions actually, that they're invariant under that foliation, in other words, they're pulled back. In other words, if you look at the derivative along the leaves of that degeneracy foliation, then that's equal to 0. That's just a check. And then you can even understand it this way, so that if you look at xij as being, if you like, a standard coordinate on space of skew symmetric matrices, then these functions are given by. So this is actually the most remarkable thing is that this works in all dimensions as well, which posed another question, which so some of the authors and other co-authors answered a little bit later about how you understand the higher dimensional versions of this. But for the moment, just let me say that this is, if you like, the first explicit example of something we've been talking about for 40 years without actually having a good example. Well, of course, there are examples of parabolic ones, where punctures on P1. But it's kind of remarkable that I always told my students, if you write a paper, have some examples, have some examples. And I've been writing papers all along about Higgs bundles without doing anything like this. So,
the Fi is Poisson.
Yes, that's right. These are Fi is Poisson. And I'll show you. Okay, so now, what is this? Well, actually, it turns out that it's an old integral system. That first of all, the integrable system is invariant under tensoring if you take the vector bundle and you tensor it by a line bundle of order 2, then that doesn't change the Higgs field. Right? So the Higgs field, if you like, lives in the adjoint representation. So actually, first of all, this really lives on the quotient of the intersection of quadrics by the involutions given by tensoring by L. But it also actually is invariant under the involution on the genus 2 curve, the hyperelliptic involution. So it comes down to something which is actually very familiar. I didn't realize this until I wrote a preprint about it, and the referee pointed it out. But this is effectively the Garnier system. That if you write it in this form, then that the Jacobian is the Jacobian of a hyperelliptic curve, genus 3. But when you want to understand this as being on the cotangent bundle of the intersection of quadrics, then it's a finite covering of that Jacobian, obviously, because we divided out. So there's an example. If you want to see an example, there's one, and you can do various things with it, as I hope I'll do in the other talks. When we get to a point, I'll say, well, what does it look like for the intersection? Okay, but then the main thing was main thing I want to address is this. Well, okay, that's all very nice, but what is it to do with the Hyperkähler metric? Because when I started this whole thing out, then it was because I wanted to use the Hyperkähler quotient construction to produce a Hyperkähler metric, just as we did for monopoles. And this was this was a sideshow. So, I mean, in the paper, I wrote something about the integrable system and about Lagrangians in it and how you could think of caustics, because I guess I'd heard some talks by Arnold in Oxford on caustics and Lagrangians, but it was there for information, entertainment. It didn't seem to have anything to do with my main purpose, which was to study the natural geometry on this moduli space. So since then, there have been a number of aspects of this moduli space, which actually bring to light this. So let me go through them. Well, first of all, there's the asymptotic metric. So if you rescale the Higgs field, so that on the moduli space of Higgs bundles, there's an obvious action of C star, just rescaling it. So it's a non-trivial action, usually. I mean, there are fixed points. But if phi is not nilpotent, then if you like, the characteristic polynomial is not identically x to the n. And so, as you rescale it, you rescale the coefficients of the characteristic polynomial, which means you are going out to infinity in the base of the integrable system. So you're going out in certain directions to infinity in this moduli space. So the Jacobian doesn't really change because all you're doing to the spectral curve is taking different coordinates. So clearly the spectral curve is there at infinity. And it's, okay, and so in the past 10 years or so, starting, I should say, with the work of Andy Knightsky in Austin, that a number of people have been looking at the asymptotic behavior of the metric. So we can't write down the metric in the way that Atiyah and I wrote down this monopole metric, but you can look at the asymptotic behavior. So it started, I think, seriously in the mathematical community with this paper of four-author paper. But there's been a lot of work since, and in recent years, Mochizuki has been involved in it. So this is called this limiting metric is called the semi-flat metric. So let me just mention what a semi-flat version of the Higgs bundle moduli space looks like. So here is basically what a semi-flat metric looks like in coordinates. So we have, omega ij is a constant symplectic form. We have a omega 3 and omega 1 of this hyperkähler metric are given by our constant, if you like, given by that formula. We have xj and xij as coefficients. But the third symplectic form, omega 2, is given by a function, the second derivative of a function. Of course, it's not an arbitrary function. These two forms and their inverses and the metric which they produce has to be hyperkähler. So obviously there's a nonlinear equation for f. So first of all, what does it mean geometrically to say that this semi-flat metric involves a constant symplectic form? So the picture is this. So we still have the integrable system. So you can think of that, the base of that as being, if you like, the space of spectral curves. It's the space of coefficients of the characteristic polynomial. So a point in the base is a spectral curve. And so if you look at there's a hypersurface inside there, a discriminant hypersurface, which consists of singular curves. So in the complement of that, you have a non-singular curve. The fiber is a torus. It's the Jacobian or a Prin variety of the spectral curve. And so if you look at the cohomology of that, then that has a flat symplectic connection. So this is the Gauss-Monnian connection. Basically, it's just homotopy invariance of cohomology. If you have a contractible disk in the base, then you can identify naturally by restriction the cohomology of any fiber with the cohomology of a fixed one. That's a flat connection. So the fact, and not only that, but the H1 of a complex torus is a symplectic manifold, a real symplectic vector space. And so this is a flat vector bundle of symplectic vector spaces. And that's really what these omega 3 and omega 1 are. And what about F? Well, what F satisfies these equations. So the F in this case is basically given directly from the spectral curve. The spectral curve has this expression. You can think of X in two different ways. I usually think of X as being the tautological section, the pullback of the canonical bundle to its total space. On the other hand, you can also think of it as being the canonical one form on the cotangent bundle. If you think of it from that point of view, then the function f, which generates this semi-flat metric, is given directly by theta wedge theta bar integrated over to that spectral curve. So this is, I mean, this is a version, mathematical version, but these sort of equations are kind of familiar. So I should say that this underlying structure is called, in the physics community, it's called a special Kähler metric. And then this sort of expression is quite familiar in that context. So, yeah, so actually, so what I observed was that, well, it's not much of an observation, is that this function actually is well defined on any spectral curve. It doesn't have to be non-singular. So the question comes about well, what happens to this structure, this semi-flat metric, as your curve becomes singular? And so what I wrote a paper about this where I pointed out that when you have nodal spectral curves, then you have actually a subintegrable system where the fibers are the Jacobians of the normalization of the curve. And that I just looked at an example which showed that it wasn't so much the function f, so f can extend as a continuous function to nodal spectral curves, but it was the flat connection that goes wrong. Flat connection has monodromy around the discriminant locus. So actually, so here's a more recent version of a paper on this issue. Here they prove that actually this is a logarithmic connection that appears here, so that it has a singularity. The flat connection is a singularity transverse to the smooth parts of the discriminant locus, but on it, it's a perfectly good connection along it, which makes sense because the subintegrable system itself is going to have one of these semi-flat metrics associated with it. Okay, so that's one aspect. This going out to infinity, we see the integrable system there in terms of the whole integrable system restricted to the smooth curves defines this semi-flat Kähler metric. Okay, so now perhaps the most famous recent work on this is the P equals W conjecture. So this is not something I'm very familiar with, but it's been an important aspect. So now you have to remember that this Hyperkähler metric has different complex structures. We've heard about this with Brian Collier's talks. So I call them IJK, and so I, for me, is the complex structure on the moduli space of Higgs bundles. This is the one which has these compact subvarieties, these tori. And J for me is the character. So the non-abelian Hodge correspondence tells you that there's an alternative understanding of these spaces as complex manifolds, where J is the character variety. In fact, everything except, if you like, 2 points, the 2 poles on the two-sphere, there's a whole two-sphere complex structures, and everyone except the 2 poles is equivalent to this character variety. So if we pick J, we look at I. These are very different as algebraic varieties. So I, which Simpson's notation is M dull, has compact subvarieties, but the character variety M Betty is an affine, no compacts, apart from points. So the P, what is the W and what is the P? So the W is the weight. So we have 2 different algebraic varieties, diffeomorphic, but with different algebraic structure. So the weight filtration is the filtration, the mixed Hodge structure on MB on the character variety. So that has that's a filtration of the cohomology, where instead of having PQ decomposition on the whole cohomology, it's on quotients, on the graded object. And what is P? So P is the reverse Leray filtration on the Dolbeault. So we have the map giving the integrable system, and then there's a filtration of cohomology given by this map. And so the conjecture made by these 3 in 2012 was based, in fact, on work of Housel by looking at the character variety over a finite field. So anyway, they made this conjecture that these two coincided. So this perverse Leray filtration has so Migliorini showed that it had actually a more concrete form. That you look at a general affine subspace of the base, you look at the way in which the cohomology restricts to the inverse image of a general affine subspace. So here, if you like, here what we see is what you could call a shadow of the integrable system in the algebraic geometry of the character variety as represented in its cohomology as an algebraic variety. So that's quite remarkable that there's something there within the character variety as an affine variety, which is reflecting this projection. And so there are ultimately there were two, I think there are probably more proofs now. So this was maybe it's a good place to look for a background, and this Seminar Bupaki paper by Vicky Hofstein. Okay, so now I want to talk about deformations of the metric. So it appears, or the functions, these coefficients of the characteristic polynomial, they appear when we're trying to deform the Hyperkähler metric. So what do we have? We've got a Hyperkähler metric of these complex structures I, J, and K. The metric is completely determined by the two forms, the symplectic forms, omega 1, omega 2, omega 3, because you invert omega 1 and apply it to omega 2 to get an endomorphism, which is K. You don't need the metric as an extra piece of data. Everything involves these three two forms, symplectic forms. And what is the equation that they need to satisfy to be an infinitesimal variation of a Hyperkähler metric? Well, it's that they should be closed and of type 1, with respect to all complex structures, I, J, and K. So if you're in 4 dimensions, if you're in R4, then a closed two form of this type would be called an anti-self-dual two form. So these satisfy some equations. In 4 dimensions, it's the self-dual. Well, these are just it was if you like the abelian self-dual Yang-Mills equation. But the notion makes sense in it makes sense in Hyperkähler geometry. And if we thought of these as being the curvatures of a connection, then on a line bundle, then we would say this is a hyperholomorphic line bundle. That's a notion which will come later. And so one way of looking at this is to look at it from the point of view of complexification. So a Hyperkähler structure is basically a reduction of the holonomy from SO4n down to SPn. The unitary group preserves I, J, and K. So over the complex numbers, if you tensor the cotangent bundle with complex numbers, then this is a complex symplectic vector bundle tensored with a trivial vector bundle H, which is basically the two-dimensional space C2, thought of like as the quaternions acted on by SU2. And so this is a complex symplectic vector bundle. So if we look at we symmetrize E and then skew symmetrize H, which just leaves a one-dimensional vector space, then that lives inside the skew symmetric forms. So there's some skew symmetric forms which are of this type. On the other hand, if we symmetrize E and symmetrize H, then that lives inside the symmetric tensors. That's 2 of T star. That's where metrics lie. So the point here is that if you want to look at the variation of a metric, then it's given by these variations of the two forms by a formula like this. So, if we think purely in terms of Hyperkähler metrics as being solutions of the Einstein equations, then G dot satisfies the Lishnerowitz-Laplacian equation. Here we've got two forms. We've just got closed two forms satisfying the analog of the self-dual Yang-Mills equations. This is the way they fit together. And so if we have the moduli space of Higgs bundles on C, then it has a complex structure, which varies as you vary the complex structure on the curve C. This is what we've been hearing about in Brian's lecture. So the tangent vector to the space of complex structures on C gives a deformation of the first order deformation of the Hyperkähler metric. So in the non-abelian Hodge theory, so the relationship between, if you like, the character variety and the Higgs bundle is that this nabla A plus phi star is a flat connection if A and phi satisfy the Higgs bundle equations. And so the point there is that the character variety, the complex structure and the character variety is independent of C. It only depends on the fundamental group. So that's independent of the complex structures. And in the omega 1, omega 2, omega 3 picture, the Goldman symplectic form is what omega 3 and omega 1 are, the symplectic form and the character variety. So when we deform, we can think of that as being fixed, which means that the first order variations of omega 3 and omega 1 are just 0. So it's just omega 2 which is varying. So this is where we bring in this the circle action here, this isometric circle action. So this is holomorphic. This is the rescaling of the Higgs field. This is a holomorphic action in complex structure I, and it preserves the Kähler form. It generates a vector field X, and the moment map is basically the norm squared of the Higgs bundle. Or in the, okay, let's just think, for the moment, let's just think of it this way, as the norm squared, L2 norm squared, global L2 norm squared. I'll be talking about this function in the next talk. And so one of the key features is that actually omega 2 this function is on the one hand a moment map for a circle action for symplectic form omega 1, but for complex structure J, then it generates omega 2 by buying up a Kähler potential. So it has these two roles in life. It's a Kähler potential for omega 2, and it's a moment map for the circle action for complex structure I. And so the upshot of this is that if we take the character variety as a complex manifold that's fixed, then everything is determined by, the whole matrix is determined by this single function. And not only that, but so the first order variation of omega 2. So this has to be a 1-1 form with respect to all complex structures. It appears here, of course, as a 1-1 form with complex structure J, but it's also a 1-1 form with respect to all the other complex. So now one needs to understand the variation of this function as you vary the complex structure. And so you could rewrite it in this way. So this is where I haven't split it up into phi plus phi star. So we have this form phi, and F is given by this integral here. So star is the Hodge star operator defined by the conformal structure, which is equivalent to the complex structure on C. So we want to fix a particular point in the character variety and vary F and see what its variance is. So, but fixing a point means fixing the gauge equivalence class of this flat connection, and then vary the complex structure. So fixing the gauge equivalence class means taking when we vary the complex structure, we take there's a corresponding infinitesimal complex gauge transformation. And then you do a calculation. You look at the variation, first variation of F, and then you use the equations that fix the gauge equivalence class and an integration by parts and the equations for a Higgs bundle to reduce those terms in these phi dot terms to this. So now everything depends just on the variation of the conformal structure. That is, okay, so star squared is -1, that's the complex structure, so star dot, star is that. So basically this is this is a representative of the, so star dot is a 0, 1 form with values in the tangent bundle. That's a representative of this Kodaira-Spencer class, which measures the deformation of the complex structure. And what is that? It's that trace, so it's basically the real part of mu, this class in here, evaluated on trace of phi10 squared. So in the usual notation, it's trace phi squared. So this is, if you like, mu applied to trace phi squared is one of the functions of the integrable system. So it's a quadratic one. The integrable system in general involves the other coefficients of the characteristic polynomial. So we can understand the variation, first variation of f in terms of this trace phi squared evaluated on. And so, but it becomes, it's part of a complex. So trace phi squared is complex. So there's a corresponding imaginary form of this. And this, so this is a Hamiltonian function of the integrable system. So d of f dot plus ig dot is equal to, so z is the vector field, the holomorphic vector field, which is generated by this complex function mu trace phi squared. So now I don't want to go line by line through this, but basically this is a using I, J, and K. You see that this, so this IZ omega 2, which is this F dot, this is giving us the deformation, actually has another incarnation as IZ, as a differential of IZ omega 1. So this is the 1, 1 aspect of it. We know that omega 2 was of type 1, 1 with respect to J, but here is the way it's expressed as type 1, 1 with respect to I. So these calculations using I, J, and K effectively reflect that property of the deformations of the first order deformations of the Hyperkähler. So now we have this, so what does this say? This says that actually, if just from the point of view of cohomology classes, that the that IZ omega 1 is a class, represents a class in the elbow cohomology H10, and the Kodaira-Spencer class is obtained by applying, if you like, the Poisson structure, taking the derivative of this, applying the inverse of omega 2 plus 3, the Poisson structure, to give the variation by Kodaira-Spencer. So here's the remark of this, it kind of worried me a little bit, that how do we, in general, when you're deforming a complex structure, you have these Kodaira-Spencer classes, but they have to satisfy a non-trivial constraint. You take the bracket. In H2 of T. If you do that for these, then there's the fact that it's closed in type 1, 1 actually means that this bracket vanishes. I won't go line by line, but basically this term here vanishes. You see, this is a Poisson structure with respect to the complex structure I. We're evaluating it on the wedge product of two forms which are of type 1. So this is a 2-2 form with respect to all complex structures. So you have a 2-0 form with respect to one complex structure evaluated on forms which are of type 2-2 with respect to all complex structures, and that has to vanish just by algebra. So these do automatically satisfy that. Okay, so now I have, so perhaps the most interesting thing, which again comes from physics, is the aspect of mirror symmetry. So the torus fibration is an example of a special Lagrangian fibration. So the Higgs bundle moduli space fits into the SYZ mirror symmetry format. And the way it does is kind of proven or validated, if you like, by this paper of Donaghy and Pantev, who looked at general Lie groups and interpreted the mirror moduli space for a simple group G as the moduli space for the Langlands dual group. And so then one of the aspects of the mirror symmetry is that the mirror symmetry between branes of different types. So a BAA brane is a holomorphic Lagrangian submanifold together with the flat line bundle in complex structure I. And a BBB brane is supposed to be a hyperholomorphic bundle supported on a hyperkähler submanifold. Hyperholomorphic being it's a connection on a bundle which has curvature of type 1,1 with respect to I, J, and K. And mirror symmetry is supposed to interchange these two. And so for me, there have always been issues about this. I mean, one is that it's very difficult to find hyperkähler submanifolds. We could take a subgroup, but then if you're not careful, then you can have a big singular locus. Or you could take fixed points of an automorphism of curve C. Each of those are hyperkähler submanifolds. When it comes down to hyperholomorphic bundles, well, I know one which comes from the hypercohomology. So if you take any representation of the group G that you're looking at, then there's a corresponding vector bundle, and there's this gives this sequence of sheaves as a hypercohomology group. And because of the way you could reformulate this in differential geometric terms, you see that it actually has a hyperholomorphic connection. In a particular case is the adjoint representation, which gives the tangent bundle. And then we also know that the universal bundle over a point, that is hyperholomorphic. But it's always seemed to me challenging to believe that any holomorphic Lagrangian is going to give something like this. Because there are simple examples. You just take one fiber, then that corresponds to a point in the mirror. So the mirror is the space of line bundles on the dual torus is the space of line bundles on the given torus. We had some years ago some experiments with character varieties of real forms. The split real form is supposed to give the trivial. So the split real form is Lagrangian. So this is what's called nowadays the Hitchin section. And this is it corresponds to the trivial line bundle over the dual, over the Jacobian. And then there's some work on real forms. So there's one case of SUNN which seemed to work, but actually all of these things there's no kind of construction of these. So what we do is to see if the data on the smooth fibers corresponds, and if they correspond to some hyperholomorphic bundle, then we know that the hyperholomorphic bundle should be well defined, and then we consider that as justification for the correspondence. So it's not as if the mirror symmetry gives you a constructive way of doing these things, although by and large you're thinking in terms of a Fourier-Mukai transform. So now this paper with Thomas Hausel gave us some examples where we did Hecker transformations on this Hitchin section, where the hyperholomorphic bundle was a tensor product of exterior powers of the universal bundle. So typically this mirror symmetry produces vector bundles of very large rank. And finally, let me finish with this final example. And what I've just shown you was that actually a deformation, this omega 2 dot, was of type 1,1 with respect to all complex structures. So this is an exact 2 form of type 1,1 with respect to I, J, and K. So it defines me a hyperholomorphic line bundle with first Chern class 0. So the cohomology class of this is 0. So the question is, does mirror symmetry work here? What Lagrangian is its mirror? And it turns out that there's an obvious one. So what we saw was that actually this, we associated to this 2 form, we wrote it as D of IZ omega, which is a 0,1 form. So you can look at this as this D bar on the trivial bundle plus IZ omega 1 defines a holomorphic structure on the trivial line bundle. And what is it? So what we have to do is the actual trivial bundle in the mirror is the section, this Hitchin section. IZ, so the Z is tangential to the abelian variety. omega 1 restricts to some multiple of the generator of the cohomology. And so this is just the way that you translate line bundles on the variety, on the Jacobian variety. So all we're doing is we're taking this vector field Z, and we're integrating at time t to t at time t equals 1 via holomorphic Hamiltonian diffeomorphism. So we're going to get a Lagrangian submanifold here just by pushing the trivial bundle, which is this Hitchin section, by this transformation. This is a very convincing way of using this particular hyperholomorphic bundle. And of course, what it means is that if you take any Lagrangian which corresponds in some way to a hyperholomorphic bundle, you can tensor the hyperholomorphic bundle by this line bundle. And that will correspond to pushing that Lagrangian around with this translation. So there's more freedom in finding Lagrangians than perhaps we thought before. And it all comes from understanding these first-order deformations as hyperholomorphic line bundles, which are determined by the integrable system. So that's it for today.
Thank you, Nigel, for the wonderful lecture and wonderful talk. Questions for Nigel? Well, I have a question. So in your early work, many years ago, you work on twistor theory. That was inspired by Penrose's work and so on. And I wanted to ask you, there is a twistor space here, referred as the Lin-Hitchin space, right? And can you say something about the role that twistor space plays in here, either in relation to the Hyperkähler structure or in relation to the integral system or whatever?
Yeah, so the twistor theory was really what got me started. I mean, in the paper with Martin Rocek and the others, they were using some supersymmetry operators with a parameter which I understood in terms of twistor theory. So for me, I knew that Hyperkähler geometry could be expressed in terms of a twistor space. And so I wanted to understand the Hyperkähler quotient in structure in twistor terms as a holomorphic symplectic quotient. And then that kind of carried on through most of the work. So there was this, I've always tried to see what the twistor version of something in Hyperkähler geometry was. So there's this thing about there was another hyperholomorphic bundle which related to passage from a quaternionic Hyperkähler manifold to a quaternionic Kähler manifold. I wrote a paper about the twistor interpretation of that. So that's always been in the background. It doesn't seem to me to appear very, okay, so where should I put it? I don't think, as yet, I can see a link with the integral system and that twistor geometry. The aspects, obviously, the asymptotic metric has a twistor space, or the semi-flat metric has a twistor space, which is, okay, the construction of that sort of twistor space is in the paper. It was something the physicists did before we wrote the paper. But for this sort of thing, no, it's somehow in the background. I mean, it's like you're looking at, well, how should I put it? I suppose if one really looked at the behavior, not just looking at J, but looking at the C star action, which takes J close to I, one might be able to see more clearly that. So, okay, so rather than looking at a single flat connection, looking at the family of flat connections or the lambda connections, that's perhaps when you might see some aspect of the twistor theory appearing. But by and large, I don't see it in this type of thing.
Thank you. Other questions?
Yeah, so, sorry. So So can you say again? So you're going to flow this, like the section by this vector field, time 1, and get a new Lagrangian. What, I think you were saying something about how the mirror changed. Were you, so can you say that again? Or
Oh, by
what is happening on the other side
you
to
should
this
be
new Lagrangian?
tensoring. I mean, so if you got one Lagrangian which corresponds to a hyperholomorphic bundle, then tensoring by this line bundle given by the deformation two form is equivalent to shifting the Lagrangian by this translation. That's the idea. So tensor product goes into shift. I mean, maybe there's a larger point of view where one can understand what's happening there. That's what seems to be happening. Yeah, so it's just a reinterpretation of this deformation two form as the curvature of a line bundle, hyperholomorphic line bundle.
Section? You could do this for any Lagrangian?
Yeah, that's the point.
So if you do it for the irreducible component of the nilpotent cone, I think it's preserved by that flow. Is that?
Well, we don't know what. Oh, if irreducible.
Yeah, one of the irreducible.
So that corresponds to a point on the other side, doesn't it? Yeah. So you just translate that point. Yeah. So yeah, it seems to work on lots of levels.
Or actually other Lagrangians that correspond to representations of surface of the group or fundamental group into some other real form, right?
Yeah.
Not just 18 section.
Yeah. So yeah. Well, we only know the real form one. We only know one example.
But already that example.
But in principle, that should be So why would you want to translate real form? Well, it ceases to be real, of course, but then tensoring with the line bundle ceases to give you the structure that you want on the hyperholomorphic bundle. Yeah. I mean, it's an observation, really, but well, it's it's kind of just support, if you like, for the idea, which seemed to be outrageous to begin with, that there might be this correspondence.
More questions?
So this is also a question about the mirror symmetry. So for usual Kähler manifolds, there's the 2D mirror symmetry. The statement for branes is a statement saying there's some equivalence of categories. The Pokai category of A branes is equivalent to the category of B branes. I was wondering, is there a statement of a similar type one can hope for Hyperkähler things?
Well, I think Babitsky and others have kind of tried to talk about hyperholomorphic. I think the thing is that, the notion of hyperholomorphic is one for a connection. So you can't have like non-trivial extensions. I mean, it's either a direct sum. It's like a unitary connection, effectively. Somehow my feeling is that you'd have to relax. I mean, so you have to accept the possibility that, the hyperholomorphic connection is a representative for something which has a bit more flexibility, canonical representative. And that if you really understand better the flexibility, I mean, of course, hyperholomorphic bundle means it's holomorphic bundle on the twistor space. So you could say, okay, well, let's just do, sheaves on twistor space, but that's commonly, I mean, twistor space is very difficult as a complex manifold. It's not algebraic. It's not. So, in principle, you don't really have that flexibility of moving things around in twistor space. Ultimately, I think if you think of these things as, canonical, like special Lagrangians, they're supposed to be canonical representatives of Lagrangians. And maybe there's a way of doing that, relaxing some of the integrability conditions, moving things around. I mean, the Fukaya picture is, of course, very, it's, when you do this, when you have a Lagrangian, the Fourier-Mukai type of transform is that you have a Lagrangian, if it intersects the fibers transversely, then okay, the vector bundle you're going to get is the direct image of the, so that's like it's a vector space, so it's a morphism, if you like, from one Lagrangian to another. You're looking at sections of a line bundle on the intersection points. They form the, of course, when you do that, you get a vector bundle, but you don't necessarily know that it's hyperholomorphic, which is perhaps another reason for thinking that hyperholomorphicity is a normalization, a canonical representative of anything else. Thanks.
So in one of the earlier slides, you've mentioned the asymptotic metric on the moduli space. And so is it unique or does it depend on how lambda goes up to infinity?
Does it depend on how? Sorry, I didn't quite get that.
I mean, one of the earlier slides, you have mentioned the asymptotic metric on the moduli space.
Yeah.
And so is phi is not nilpotent then. So then is it unique?
It's an approximate metric, so it's I mean, yeah, it's you know, I mean, many of the proofs about its degree of approximation is that it's trying to find an exponential fall off in a certain sense. So originally there was some power series fall off, but finally it was but it's unique. I mean, there are no choices to be made there, but nevertheless it's the terms you ignore. You know, they could be different, but it's based on the same. Yeah, so if you like, it's based on the same algebraic integrable system. So you might ask the same question, could the same could an isomorphic integrable system give you the same, extend to the same Hyperkähler metric? And so is the Hyperkähler metric uniquely determined by the integral system? I mean, that's a good question, actually. If there is one, complete with all the properties that we know, is it determined by the integral system? That would be a valid question.
A little bit of a vague question. So is it known what kind of Hyperkähler manifolds can be realized as Higgs bundles? And also what kind of integrable systems can be realized as Higgs bundles, moduli space of Higgs bundles, sorry.
Yeah, so that kind of relates to the question about in a way what I'm going to talk about tomorrow, where I use the C star action or the circle action. And I'm in a particular way. And I was looking for other examples of Hyperkähler metrics where the same sort of thing happened. So, of course, there are plenty of Hyperkähler metrics with a circle action of this type. There aren't so many where the complex structure for J, if you like, or for the other ones, is where there's how should I put it? Where that's fixed. So for example, if you take resolution of a resolution of a Kleinian singularity. So you take this these Hyperkähler 4 manifolds. Then the general fiber. So we have special fibers which are analogous to the Higgs bundle picture. The generic fibers are affine varieties, but as affine varieties, they still have moduli in that case. So that's not the same. So if you like, when you deform, you deform the three true forms. I mean, this is what we know, and there's actually a Torelli theorem. So so looking for Hyperkähler manifolds which are not of the Higgs bundle type is a little difficult. I mean, looking for ones where 2 of the 3 forms are actually fixed, and the only one there is. I mean, it's how should I put it? It's It's like this question about, are all integral systems special cases of my system? I mean, yes and no, yes and no. It depends on when you look at it. But, I mean, that's the kind of question that's floating around. And so you might say when you see an integral system, if you can, you know, which is not obviously, you know, related to one of these, then maybe there's a Hyperkähler metric that goes with that, which isn't. One might also say that you can translate every one of those functions. I was just looking at the quadratic function, and if one of those functions gives you a translation in the Higgs bundle moduli space, and so, and even when you look at the deformations of the semi-flat metric, you see that you get deformations just by. So this is a question which is we were discussing over lunch. It's possible that there are deformations of the Hyperkähler metric, which are outside of deformations by the curve. That will be a new type of metric. So I mean that is something which is worth exploring.
Okay, so I think we look forward for more phases of Higgs bundles tomorrow. But now there is a high tea waiting for us, but before that, thank Nigel again for this beautiful lecture.